At 1917 UTC on June 8, 2026, a cannibal coronal mass ejection, a merged structure of two separate solar eruptions, one swallowing the other in open space before impact, struck Earth's magnetosphere and drove a G3 geomagnetic storm classification, pushing auroras, visible to naked eyes in France, New Zealand, and latitudes that have not seen solar light displays in years, while simultaneously inducing currents in long-haul transmission lines at high latitudes that forced voltage corrections and protective switching maneuvers on grids across northern Canada, Scandinavia, and Alaska. And this morning, June 10th, 2026, the residual magnetic disturbance continues. The active region responsible for the eruption sequence, NOAA sunspot region 4455, remains on the solar disk, magnetically complex, and capable of producing additional significant flares before it rotates beyond the western limb. If you rely on this channel for science-grounded and verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the European Seismic Center, and peer-reviewed research published in Space Weather Journal. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed. The data is public. The responsibility to check belongs to all of us. But that is not even the complete picture. What struck Earth 2 days ago is not simply a space weather event. It is a chapter in a longer story that the Sun has been writing across solar cycle 25, a story that began exceeding all expert forecasts as early as 2023, and that has been building, accumulating, compounding, returning again and again to Earth's doorstep, through a period that space weather researchers have now characterized as a window of sustained elevated risk for satellite infrastructure and high-latitude power grids, extending from early 2026 through at least mid-2027. The June 8th cannibal CME is not an anomaly. It is a data point in a pattern, and the pattern is the warning. To understand what just happened and what the instruments are still measuring this morning on June 10th, 2026, you must understand what a cannibal coronal mass ejection actually is, because the name carries weight that the public record has not yet fully translated into plain language. A coronal mass ejection is a billion-ton eruption of magnetized plasma expelled from the sun's outer atmosphere at speeds that, in extreme cases, exceed 3,000 kilometers per second, fast enough to cross the 150 million kilometers between the sun and Earth in as little as 15 hours. In the events leading up to June 8th, active region 4455 produced 3 significant eruptions in close succession beginning on June 3rd, an M9, 3 flare at 0136 UTC, and M7, 7 flare at 07 UTC, and an X1, 0 flare at 1128 UTC, 3 separate eruptions, 3 separate walls of solar plasma launched toward Earth. When a faster CME is launched behind a slower one already traveling through interplanetary space, the faster structure overtakes and merges with the slower one. Physicists call this complex ejecta. What arrives at Earth is no longer 2 separate events. It is a single merged structure carrying the combined magnetic energy of both eruptions, with an internal magnetic field orientation that is substantially less predictable than any single source CME. That unpredictability is significant. The coupling efficiency between a CME's magnetic field and Earth's own magnetosphere depends critically on the orientation of that field. A southward-facing component in the incoming solar wind locks onto Earth's northward-facing magnetospheric field and transfers energy with extreme efficiency. And because complex ejecta has that less predictable field orientation, forecasters cannot know in advance whether the impact will remain at G3 or push toward G4. On June 3rd, NOAA's Space Weather Prediction Center issued a G3 strong geomagnetic storm watch for June 4th and 5, describing the 3 Earth-directed CME components identified from region 4455, which had been observed with an anti-hail magnetic configuration, continuous magnetic flux emergence, mixed polarities, and substantial magnetic shear. These are the signatures that indicate an unstable region, a region that is not finished speaking. NOAA's forecast, issued June 6th, predicted CME impact by midday UTC on June 8th. The shock arrived within hours of that prediction, a forecast accuracy that space weather scientists themselves have highlighted as a marker of progress in CME propagation modeling. For every additional hour of advance, warning a grid operator receives, protective switching maneuvers become easier, and transformer damage becomes less likely. The accurate forecast on June 8th mattered. On the day that forecast fails, it will matter more. Here is where this account becomes genuinely significant. The physical structure of Earth's modern power grid was not designed with geomagnetic storm resilience as a primary engineering requirement. It was designed for a different threat profile entirely, for load fluctuations, for lightning, for mechanical failure. The vulnerability to geomagnetically induced currents, known as GICs, arises from the basic geometry of the system, thousands of kilometers of high-voltage transmission lines running across the surface of the ground, connected through transformers to generating stations, forming a continental-scale conductor that sits in direct contact with the geomagnetic field. When a solar storm disturbs that field rapidly and over a wide geographic area, it induces direct currents in those lines, currents that transformers were not built to carry. At G3 intensity, the documented effects include voltage corrections on power systems, false alarms triggered on protection devices, surface charging on satellite components, and increased atmospheric drag on low Earth orbit spacecraft as the upper atmosphere expands under solar heating. These are the confirmed effects at G3. They are manageable, but they are not trivial. And the question is not whether a storm capable of overwhelming those management protocols will arrive. The question is when. This is not a hypothesis. This is documented in the geological record, and more recently, in the engineering postmortems of the events that shaped how grid operators think about space weather. On the morning of March 13, 1989, a geomagnetic storm classified at the extreme KP index of 9, the maximum on the standard scale, a G5 event, struck Earth with a DST index of negative 589 nanoteslas. To put that number in physical terms, the DST index measures the deviation of Earth's horizontal magnetic field at the equator in nanoteslas. A storm that pushes the DST to negative 589 has distorted Earth's magnetic field by more than 580 units from its normal resting value, the field lines that hold the magnetosphere. In place were compressed on the sun-facing side and stretched outward on the night side in a configuration so extreme that aurora was observed as far south as Cuba. At 7:45 Universal Time on March 13, 1989, Hydro-Québec's power transmission system, the James Bay network, went offline. Not gradually, not with warning sufficient to prevent cascading failure. Within 90 seconds, automatic protection systems tripped relay after relay, shutting down 21 gigawatts of electrical supply, 6 million people in the Canadian province of a province that covers twice the area of the state of Texas lost power. They lost it in the dark of a Canadian winter morning before most of them had made their first coffee. The blackout lasted 9 hours. The material damage to equipment from induced overvoltages cost Hydro 2 million Canadian dollars, with 5 million of that in physical equipment alone. A single high-voltage transformer in New Jersey, damaged in the same storm by the same GIC mechanism, cost $10 million to replace, and the critical detail that the engineering literature documents clearly in the United States, more than 200 grid faults occurred within the first few minutes of the storm's onset across the interconnected northeastern grid. Grid operators were able to manage around those faults. But the margin was not wide. Think about the city of... On the morning of March 13, 1989, 1.5 million people in the metropolitan area, hospitals mid-procedure, apartment buildings with electric heating in the final months of winter, metro trains stopped in tunnels. It was not a war. No bomb fell. No infrastructure was targeted. What arrived was invisible. Traveling at several hundred kilometers per second, indistinguishable from empty space to the naked eye, a disturbance in a magnetic field that most people do not know exists. And 6 million people discovered, over 9 hours, how much of modern life depends on the continuous flow of electricity through lines they have never seen. That event was rated G5 on the modern NOAA scale. The storm that struck Earth on June 8, 2026 was rated G3, but what the March 1989 record teaches is not that G5 is catastrophic and G3 is manageable. What it teaches is that the gap between manageable and catastrophic is narrower than the scale implies, and that the factor which determines which side of that gap an event falls on is not storm intensity alone. It is the combination of storm intensity, duration, the magnetic orientation of the incoming plasma, the specific geography of exposed grid infrastructure, and the preparedness state of the operators managing that infrastructure in real time. The system is not inactive. It is accumulating, and the sun that produced the June 8th cannibal CME has not finished its current period of elevated activity. Solar Cycle 25 officially reached solar maximum in October 2024, when NASA and NOAA announced that the smoothed monthly sunspot number had peaked at 161, a value that exceeded the predictions made by the International Solar Cycle Prediction Panel in 2019, which had forecast a peak between 105 and 125. The cycle had been expected to be moderate. It was not moderate. It produced more sunspots, more M-class flares, more X-class flares, and more Earth-directed CMEs than the forecasting panel anticipated. In May 2024, a G5 geomagnetic storm, the most intense since the Halloween storms of October 2003, drove auroras visible across North America, Europe, and parts of Australia, disrupting high-precision GPS systems used in agriculture and creating a documented $500 million impact on that sector alone, according to NASA's own reporting. That storm was the most intense in 21 years. It arrived less than 2 years ago. And the data that space weather researchers have now put in print characterizing the period from early 2026 through mid-2027 as a window of sustained elevated risk reflects the reality that solar cycle 25, though past its peak, is descending slowly and unevenly. Sunspot counts remain significantly elevated. Compared to the quiet years of 2019 and 2020, region 4455, which produced the June 3rd eruption sequence, is still on the disk. Region 4456 is still on the disk. Region 4461 is still on the disk. These are not background features. These are named active regions with documented recent flare histories under continuous monitoring by the Space Weather Prediction Center. Consider what it means to live in Troms, Norway, a city of 77,000 people situated at 69 degrees north latitude, well inside the auroral oval. During G3 conditions, Troms is at the center of the geomagnetic disturbance, not at its edges. High-frequency radio communications that local fishing fleets and coastal shipping services rely on face intermittent blackout, not signal degradation, but blackout. The HF bands go silent. And the grid infrastructure that serves northern Norway and northern Canada was built across some of the most geologically resistive terrain on Earth, ancient crystalline shield rock with very low electrical conductivity. That matters because when ground conductivity is low, the electric fields induced at the surface by a geomagnetic storm are amplified. The hydro collapse in 1989 happened precisely because the Canadian Shield, the ancient Precambrian bedrock underlying much of northeastern North America, provided almost no path to ground for the induced currents. The current had nowhere to go except into the power lines. The physics that destroyed transformers in 1989 has not changed. The rock beneath northern Canada is still the same ancient, resistive shield it was on March 13, 1989. The voltage levels in the modern grid are, in many cases, higher. The transformers are, in many cases, larger and longer lead time to replace. One critical transformer can require 18 months of procurement and manufacturing time. The manufacturing capacity for extra high-voltage transformers within North America has not expanded significantly in the intervening decades. And here is where the connected systems of this story demand attention, because what happened in interplanetary space on June 3rd through June 8, 2026 is not a space event that happened to touch Earth. It is a demonstration of how the sun, the solar wind, Earth's magnetosphere, the ionosphere, the thermosphere, and the global electrical infrastructure form a single coupled system whose behavior cannot be understood by examining any one layer in isolation. When solar wind carrying a strong southward magnetic field encounters Earth's magnetosphere, the energy transferred heats the upper atmosphere, the thermosphere expanding it outward into the orbital altitudes where low Earth orbit satellites operate. That expansion increases atmospheric drag on those satellites, gradually lowering their orbits and requiring fuel expenditure to maintain station. The Starlink constellation, which now comprises thousands of satellites in low Earth orbit and provides communications services to aviation, maritime operations, remote communities, and military users worldwide, is directly sensitive to thermospheric expansion during geomagnetic storms. In February 2022, a geomagnetic storm caused elevated atmospheric drag that led to the loss of 40 newly deployed Starlink satellites before they could reach operational orbit. That was a relatively minor storm. The June 8 G3 event generated measurable additional drag on satellites across the low Earth orbit regime, and simultaneously, the same ionospheric disturbance that expands the thermosphere disrupts the signals of the global navigation satellite systems GPS, Galileo, GLONASS that underpin modern logistics, agriculture, financial, market timing, and emergency services coordination. When the ionosphere churns under a geomagnetic storm, GPS signals refract unpredictably. Positioning errors that are normally measured in centimeters become errors measured in meters. For a container ship navigating a narrow channel, a meter is not a rounding error. The second connected system is one that requires the long-view perspective to appreciate. Geomagnetic storms of the intensity experienced this past week induce currents not only in power lines but in all extended conductors at Earth's surface, including pipelines. The Alaskan Pipeline, the Trans-Canada Pipeline, and major pipeline networks in northern Russia and Scandinavia have documented histories of accelerated corrosion attributed to geomagnetically induced currents. The induced currents create electrochemical gradients on the steel walls of pipelines, accelerating the corrosion process in a phenomenon known as stray current corrosion. This is not a theoretical risk. The engineering literature documenting GIC-related pipeline corrosion dates to the 1970s. It is a slow, invisible, cumulative effect, the kind that does not produce a news event on the day it occurs, but that contributes to infrastructure degradation over years and decades. In a period of sustained elevated solar activity like the one the data now confirms extends through at least mid-2027, the cumulative GIC exposure to pipeline infrastructure represents a monitoring and maintenance burden that is not widely discussed in public space weather communications. On June 9, 2026, the day after the G3 storm peak, NOAA's real-time data showed Earth's magnetic field ranging from quiet to unsettled KP index between 2 and 3, no G-scale storm thresholds crossed. 14 C-class flares, the category of common, background solar activity, were recorded in the 24 hours following the event. The strongest was a C4, 5 from region 4465 at 4:23 UTC. Region 4455 itself produced only a C3, 0 at 6:52 UTC on June 9. This relative quiet is not reassurance. It is an interval. The behavior of region 4455 over the preceding week an M9, 3, and M7, 7, and an X1. 0 in a single day on June 3rd, followed by the production of the CME sequence that culminated in the June 8th impact is the behavior of a magnetically complex, energetically loaded region that has not demonstrated it is finished erupting. The anti-hail magnetic configuration that NOAA documented in region 4455, the continuous flux emergence, the mixed polarities and substantial magnetic shear, these are not past tense characteristics. They describe the structural state of a region that is still rotating across the solar disk, still being monitored, still under assessment for additional eruption potential. Scientists choose their language carefully here, and that careful language is itself the warning. When NOAA's Space Weather Prediction Center characterizes a region as having substantial magnetic shear, they are not describing its history. They are describing its current state. Shear is energy stored. Energy stored is energy. Available for release. The Carrington event of September 1859 is the reference point that space weather researchers return to when they attempt to characterize the upper bound of what the Sun is capable of delivering to Earth's doorstep. The geomagnetic storm that followed Richard Carrington's observation of a solar flare, the first ever directly observed by a human being, produced a DST index estimated at approximately negative 1,700 nanoteslas, nearly 3 times more intense than the 1989 event. Telegraph systems across Europe and North America. The electrical infrastructure of the mid-19th century failed catastrophically. Operators reported receiving shocks from their equipment. Some telegraph lines operated without battery power, driven entirely by the induced geomagnetic current. When the National Academy of Sciences modeled the potential impact of a Carrington-scale event on the modern power grid in a report that the U.S. Geological Survey has cited publicly, the conclusion was a possible continent-wide loss of electricity with infrastructure damage that could persist for months, with an estimated economic cost in excess of $1 trillion. That is not a figure from a science fiction scenario. That is a peer-reviewed estimate of what the physics of a documented, historically verified solar storm would do to a grid that was not designed to survive it. The question is not whether a Carrington-scale storm will occur again. The geological and historical record confirms it has happened before. The sun that produced it is the same sun that produced the June 8, 2026 cannibal CME. What changes over centuries is not the sun's capacity. What changes is the complexity and extent of the electrical infrastructure in the path of its output. In Reykjavik, Iceland, a city of 130,000 people on an island in the North Atlantic, at 64 degrees north latitude, sitting squarely within the high-latitude zone of maximum geomagnetic storm impact, daily life runs on a grid powered almost entirely by hydroelectric and geothermal energy. The people of Reykjavik have access to a national power company, Landsvirkjun, that has decades of experience managing grid behavior during geomagnetic disturbances. They have protocols, they have practice, they have institutional memory of what a disturbed magnetic field does to their infrastructure. And still, during G3 and G4 events, Icelandic grid operators must take active protective measures, load shedding, protective switching, monitoring for transformer saturation that would not be necessary on a magnetically quiet day. Now consider that the population of Greater Tokyo, a city at 35 degrees north latitude, far south of the traditional auroral zone, connected to a grid that has not historically been considered at high risk from geomagnetic storms, numbers over 37 million people. The Japanese grid serves one of the densest concentrations of electrical load on Earth. In a Carrington-scale event, the expanditor or a lovel brings geomagnetic disturbance to latitudes that are not in the engineering calculations of grid operators who designed their systems for different threat profiles. What makes a geomagnetic superstorm different from a regional emergency is precisely this: it does not respect the latitude lines that determine which grid operators have invested in mitigation and which have not. Minutes are not hours, and in this context, that difference is everything. The hydro failure in 1989 cascaded from first anomaly to complete blackout in less than 90 seconds. The protection systems that tripped the network offline were doing exactly what they were designed to do, responding to the voltage asymmetry and harmonic generation that the GICS created in the 735 kilovolt network. The protection systems did not fail. They succeeded, and their success produced a province-wide blackout. This is the paradox at the heart of grid vulnerability to geomagnetic storms. The protection mechanisms built to safeguard equipment respond to the symptoms of GIC intrusion by isolating affected segments. That isolation cascades through an interconnected system faster than human operators can intervene. Hydro, after 1989, lowered the sensitivity of its protective relays, a calibration change that has prevented recurrence during subsequent storms of similar or lesser intensity. The United States grid is a patchwork of interconnected systems operated by different utilities, with varying levels of GIC mitigation investment, varying relay sensitivity configurations, and varying levels of real-time space weather data integration in their control rooms. The Federal Energy Regulatory Commission has issued standards for geomagnetic disturbance vulnerability assessment. Those standards exist because the vulnerability is real and documented. The gap between assessment and full mitigation remains open. What the official data actually shows, as of this morning on June 10, 2026, is a sun in the gradual declining phase of solar cycle 25 that has nonetheless delivered to G3 or stronger geomagnetic events within the past 30 days, that retains multiple active regions on the solar disk, including the same region 4,455 responsible for the June 3rd eruption sequence, and that continues to present an elevated probability of M-class and X-class flaring while those regions remain geoeffective. NOAA's own space weather researchers have placed the window of sustained elevated risk at high-latitude power grids and satellite infrastructure as extending from early 2026 through mid-2027. The June 8th cannibal CME arrived within that window as predicted. It was not the last event in that window. What distinguished June 8th from a grid emergency was accurate forecasting, operational preparedness, and the fortunate fact that the magnetic field orientation of the complex ejecta, while sufficient to drive G3 conditions, did not couple with Earth's magnetosphere at maximum efficiency. That last variable, the B's component of the incoming solar wind, the southward tilt of the interplanetary magnetic field, is the one that is genuinely difficult to predict more than 1 to 2 hours before impact. It is the difference between G3 and G5, and it is determined by the internal magnetic structure of the CME, which is set at the moment of eruption on the Sun's surface, travels invisibly across 150 million kilometers of space, and is measured by the Discover satellite at the L1 Lagrange point approximately 15 minutes before the CME structure reaches Earth. 15 minutes. That is the warning window for the variable that matters most. For a G3 storm, 15 minutes is enough to confirm what protective switching has already been prepared. For a Carrington-scale event, 15 minutes is the interval between measurement and impact, and on the day that interval proves insufficient, the post-mortem will note it clearly. The Sun has been the same object for 4-6 billion years. It has produced coronal mass ejections in the years before the first human being lit the first fire, in the centuries before the first copper wire was drawn, and in the decades before the first high-voltage transformer was installed on the Canadian Shield. It does not know the grid is there. It does not modulate its output for the convenience of the civilization that has grown dependent on electrical infrastructure that was never fully hardened against what the nearest star is periodically capable of producing. What is new is not the Sun's behavior. What is new is the density and complexity of the electromagnetic infrastructure now in its path, the satellites, the power lines, the pipelines, the GPS-dependent systems, the HF radio networks, the financial clearing systems whose timing signals are synchronized to satellite clocks, the hospital equipment that runs on uninterrupted power. What is new is how much more there is to lose, and what the data from June 8, 2026 adds to the record is not a catastrophe narrowly averted. The storm was significant but managed. What it adds is a confirmed data point in the window of elevated risk, a demonstration that the cannibal CME mechanism that produces the most energetically unpredictable impacts remains active in the current solar cycle, and a reminder that the difference between a managed G3 event and a catastrophic one is a combination of forecast accuracy, grid operator preparedness, and the orientation of a magnetic field vector that cannot be measured until the CME is already 15 minutes from impact. The system is accumulating. Region 4,455 is still on the disk. The 11-year cycle has not finished its current passage, and the geological record, which holds in its layered strata the isotopic signatures of solar particle events going back thousands of years, confirms without ambiguity that the Sun has done this before at scales that dwarf everything the modern grid has been asked to survive, and that it will do it again on a timescale that is not measured in decades but in the patient, indifferent arithmetic of stellar physics, against which the entire span of human electrical civilization amounts to less than a single sunspot cycle.